So our next presentation is going to be great work by several people from Nvidia. So Tero, Karras, who will be giving the presentation, Timo Aila, Samuli Lane, and Jaakko Lehtinen on progressive goring of GANs for improved quality, stability, and variation, and impressive images.
Thanks for the introduction, Pascal. So hi, I'm Tero Karras from Nvidia. Generative adversarial networks are quite impressive. They can turn zebras into horses, cats into dogs, dogs into smoke and mushrooms, and frowns into smiles. However, they are very difficult to train, and these techniques are usually limited to fairly low resolutions. Inspired by this, we wanted to see what it would take to scale up and be able to generate photorealistic images at megapixel resolutions. But first, we need to understand what is going on during the training. Our intuition is illustrated nicely by looking at this map showing the Finnish archipelago. The islands represent clusters of real images in the vast sea of all possible images, and we wish to obtain a generator function that produces something similar. We train the generator to shift the distribution of these generated samples closer to the real thing. Let's take a closer look at one of these dots. Our view of the situation looks like this. The generated sample is the surfer guy who is seeking the shore. Everything is governed by the loss functions, in our case, the improved Wasserstein. Most importantly, gravity is pulling the surfer down. But then we have this adversary who is raising waves wherever the surfer is. However, they cannot raise waves on the shore, and the waters have to be calm in between. So what is happening is that the surfer is sliding down, the wave keeps following them, and so they'll be able to ride it toward the shore. What is the problem with high resolutions then? Well, if the resolution is low, then both the generator and the discriminator are rather simple functions, and our picture is accurate. But if we increase the resolution, they become deep networks, and they represent complex functions with shattered gradients. So it's almost as if we had thrown the surfer in the middle of the ocean. There's waves everywhere, and the shore is nowhere to be seen. In many ways, we are now looking at the situation from too close. If we decrease the resolution, it's like zooming out. We get a much clearer view of the big picture, but we can no longer discern the smallest waves. Motivated by this, our approach is to start the training from a ridiculously low resolution in hopes that we will start making progress toward the right direction. Once we get closer to our goal, we'll then increase the resolution by adding more layers and keep going like that so that we'll be able to model finer and finer details toward the end. So that's the basic idea. Let's look at the implementation. Our generator is made up of these replicated blocks that consist of upsampling and 3x3 convolutions. We can extract a low-resolution image out of the network at any point by passing the activations through this 1x1 convolution. When we want to increase the resolution, we cannot go and add the new layers just like that, because they are completely untrained, and doing so would cause a sudden shock. So what we do instead is extract two images at different resolutions and do a linear crossfade between them to gently introduce these new layers. Once we're done, we'll scrap the low-resolution image and keep going. Our discriminator is a perfect mirror image of the generator, and both networks keep growing in synchrony using exactly the same kind of linear crossfades. Let's see how this looks like in practice. On the left, we have standard fixed resolution training, and on the right, we have progressive growing. With fixed resolution, the convergence is somewhat chaotic, and I would claim that it's not always clear whether we are making progress toward better images. But with progressive growing, even though the resolution is low at the beginning, the images still stay pretty reasonable throughout the entire process, and there's a clear tendency towards better and better results. Besides quality, we must also consider variation. What often happens is that all of our generated samples flock toward the same nearest shore, and we have a mode collapse right there. In order to avoid that, we need to have some way to force the samples apart and keep them apart throughout the training. We obviously cannot do that if we're looking at just individual pictures. So the obvious way out is to extend the discriminator to look at multiple images at once. This has been proposed before, and it's a good idea, and we build on top of it by introducing this special layer toward the end of the discriminator. The input is the set of activations from the previous layer for every image in the mini-batch. These activations are passed through as is. But in addition, we also compute the standard deviation for every activation over the images. We then average these standard deviations over the features and over pixels to yield a single scale value. We then replicate that and append it as a new feature map in the output. The surprising thing is that even though we are looking at a single statistic, it seems to be enough in practice to enforce exactly the right amount of variation. The benefit of our technique compared to previous ones is that the number of trainable parameters does not increase almost at all. There's one more obstacle to overcome, though. What sometimes happens is that the surfer stumbles a bit and accidentally ends up on the wrong side of the wave. Gravity still pulls them down, and the wave still keeps following. That's not something we want to happen. We have observed that one of the early symptoms of this scenario is rapid increase in the activation magnitudes, and also that any kind of normalization in either network is very effective in preventing that. So it's no wonder that virtually all previous techniques employ some kind of normalization, usually in both networks. In particular, they employ batch normalization, which is problematic because it requires huge mini-batch sizes, and with high resolutions, we cannot afford those. Furthermore, we have seen that smaller mini-batches are generally better in terms of convergence. So what kind of normalization should we use then? First of all, it's enough if just one of the networks is unwilling to participate in this kind of arms race. So it's enough, we can safely leave out any kind of normalization in the discriminator. Then in the generator, we employ this new normalization scheme where we look at the activations after each convolutional layer. And we treat each pixel as a vector over the feature maps and process every pixel independently. What we do is simply normalize these vectors and pass them on to the next layer. The surprise here is that this kind of normalization does not seem to harm the generator in any way, but is well enough to prevent the bad scenario from happening. Let's look at some results next. These are examples of images produced by our generator after training it with a new dataset that we call celeb-A HQ. It's based on the standard celeb-A, but we've used various tricks to improve the overall image quality. It consists of 30,000 images at 1K by 1K resolution and is available in public. We feel that most of these images are almost indistinguishable from the real ones, which is pretty nice. Since the generator is a continuous function, it's interesting to look at interpolations. Here we are varying the input to the generator randomly using spline interpolation. And what we can see is that many of the transitions look quite natural. The hair is growing and changing shape. The viewing direction and lighting conditions are changing smoothly. And the facial expressions are changing quite naturally. I would say that the generator has learned to model various characteristics of the images and is now mixing these characteristics in novel ways. Some of the transitions are still somewhat weird and look broken. And I think this is an interesting open question for future research. What exactly is causing that? We also tested our techniques using the ELSAN dataset at 256 resolution. The dataset contains 30 categories, and here I'm showing examples from 7 categories. I should emphasize that this dataset is extremely challenging because there's immense amounts of variation in all of the categories. Nevertheless, our technique was able to finish training for every single category without fail, and many of the images look quite reasonable. It's especially interesting to see some 3D rotations and zoom-ins in many of the categories. We are particularly proud that our network has learned to generate lolcats with some gibberish captions even. Our paper covers several other contributions that I will skip here, but I should mention that we found it extremely important to have some kind of a reliable metric to judge the quality of the results, especially for hyperparameter search. We didn't have any good ones when we started, so we had to invent our own. But these days, there's, for example, the Frechet inception distance, which is pretty good. Our implementation and networks and all kinds of other material are available in public. And if you have enough GPU power, you'll be able to train these 1K by 1K monster networks in 2 days. If you're interested, come see our poster on Wednesday. Thank you.
Let's take a couple of questions.
Thank you. That was very impressive. This is still very image based. Oh, sorry. Yes. This is still very focused on images, and in fact, your whole technique is based around low and high resolution images. Do you have any way to generalize this to other fields, other problems, speech, text, or anything like this?
We don't have any results on those domains yet, but we are very interested in trying it out. For example, with audio, I think you could quite easily do the same kind of progression just by resampling the audio signal. And I'm interested in finding out whether it is actually more about the resolution or the capacity and depth of the networks. It might be that even if we don't reduce the resolution of the domain, we might be able to benefit just from the fact that we are adding more depth in the networks as we go.
Any other question? Any last question before everybody goes? Yasha?
This looks too good to be true. Did other people reproduce your work independently?
Thank you. Well, reproducing it is quite easy. Just download the code and run it. I have seen implementations by other people, by Google at least, and something running on PyTorch. Haven't tested them myself.
Okay, thank you very much, Tero. So this closes our first oral session. The break, we're a little late for the break, but there's still time.